Hi folks, Mr. Ackerman here. Thanks for watching. In this video, I'm going to show you the general format that you should be following when you solve what I would call larger type problems, the kind of problems that you see on tests and quizzes or whatever we happen to be calling them. I'm making this video during the pandemic, so we've modified the way that we do the tests. They're not the huge tests that they used to be. They're going to be more numerous but smaller size things, so call them a quiz or a test or a quest or whatever you want. Here's how you should be solving your problems. There's two goals I have here. One is to let you know the way to present your solution so that when you show it to me, it communicates what I need to see to grant you the marks that you're looking for. And the second thing is, if you follow this problem-solving strategy, in my opinion, you have the highest chance of getting the question right and also gaining the highest possible marks. So it's a win-win situation. There's just a few things. Some of you I know don't want to follow this procedure because you've figured out your own procedure over the years and you think it works pretty well. If that's the case, then so be it. If it's working for you, stick with it. But there are some things you have to include, at least to get the communication marks that you're looking for. Let's take a look at the problem. You'll see what I mean, and I'll throw in some advice along the way. The question I'm going to use to illustrate this is number 10 on page 40. So in this question, there is a building, which you can see by this rectangle here. 28.5 meters above the ground is a balcony, and a flower pot, F, is dropped at time 0. There's another balcony below it, 26 meters above the ground, and on that balcony there's a ball, which is not dropped, but it's thrown downward 1 second after the flower pot was dropped. Now you might be able to see just by looking that in the first second the flower pot is going to pass where the ball starts. So basically the flower pot is in a race with the ball and it gets a head start. It gets a distance head start and a time head start, but it's only dropped. It's not moving at the beginning. The ball, on the other hand, has a disadvantage of starting a second later, but it has the advantage of being closer to the ground, and it's given a 12 meter per second boost right off the bat. Will the ball catch the flower pot? That's the question. And if so, where? So in drawing the outline of the building and the balconies and the letter F and the B for the ball, I've also put in these thick black lines to show the progress of the two objects as they go down. I want to visualize what it looks like for them to move, and then I'm going to put in this dashed line here, which shows that when they meet, well, that means they're at the same place. So I start thinking, oh, this is a position or displacement kind of question that they're asking me. Well, the next thing to do is to label all of the important information. For example, the flower pot's initial velocity is 0 and the ball's is 12. But there's two V1s here and I don't want to confuse them. So V1F for flower pot and V1B for ball. Now there's another thing. The times that they're working on are different. The flower pot begins at 0, but the ball hasn't started moving yet. It's not until the flower pot time is equal to 1 that the ball begins moving, so it's at 0. So they're always going to be offset by a second there, and I need to account for that. For the time being, I'm going to use TF or delta TF and TB or delta TB. The other thing is the acceleration, which is the same for both of these, is 9.8. It's down. Everything's pointing down in this question, so I'm just going to designate positive as down. And I think I've now explained to you what I put into the diagram. Let's just pause for a moment. Some of you are going to say immediately, this is a lot to write down and it takes a lot of time that I don't have during a test or a quiz or whatever. My answer to you is this. If you don't do this because you want to save, let's say, 1 to 2 minutes in the beginning, you're going to be short-circuiting your brain's opportunity to visualize the problem in as much detail as possible. The 2 minutes that you take to think through and draw a diagram really, really carefully is actually going to give you a head start in terms of your thinking. For 2 minutes before you begin writing a solution, your mind is working away in the background on what to do. And as you think more deeply of it, because you want to make an accurate diagram, what also ends up happening is your brain starts thinking more deeply. So in summary, here's what I'm looking for in a diagram. Reasonably accurate, fully labeled, correct symbols, units, all that stuff. Good attempt to visualize what's going on, if things are moving, showing the path, and so on. This is part of your communication mark, and it's mandatory on a question. So the last thing to say to you is, if you decide I'm not going to do all this stuff because it's just not my style, that's your choice, but it's also going to cost you communication marks. So you might as well get used to it now, and then it's going to benefit you, you're going to see in the future. Next up, let's take a look at the solution. How do you solve this one? Well, hopefully from the diagram you can see that when the thick black arrows meet, that's when the objects are at the same place and we can solve the problem. One of the arrows is longer than the other. And how much longer? Well, it's the separation of the balconies. So that immediately tells my mind this is a displacement idea, and I can write a displacement equation. The flower pot displacement is the same as the ball displacement as long as we account for the 2.5. This line is 2.5 meters shorter than this. So here's my first equation. And if you write this down with the correct symbols, any vector symbols, that kind of thing, you would receive credit for that. The second thing is we have to sub in for the delta df and delta db, because these are two variables in one equation we can't solve. So if you think about displacement when an object is falling and is released, or if it's thrown, that's an acceleration due to gravity thing. So we can use the big equation, delta d equals v1 delta t plus a half at squared. We can write it for the flower pot, and we can write it for the ball, and we can sub it in to the original equation. Now, once we do that, we come up against another problem, which is that we now have eliminated the delta df and delta db, but we have in there, annoyingly, delta tf and delta tb. Now the times are the problem, but hold on a minute. There's a relationship between those as well. I mentioned it at the start of the video, or near the start, which is that they're always off by 1 second. If you think about it, flower pot time, when it reaches 1 whole second of falling, that's when the ball time is at 0 and just beginning its motion. Now, if the flower pot has been falling for 2 seconds, that means the ball's only been going for 1. There's a 1 second difference, and you can write an equation that relates them, and that's over here. If you now use this to sub back into this one, you can eliminate one of the time variables and get all of the time variables to be the same. So at this point, I'm just going to move myself up here so I'm not in the way of the problem. And you'll see that with a little bit of algebra, there's a bracket to expand here. Remember, squaring the bracket, write the bracket twice. A little bit of algebra, and eventually you solve a pretty simple equation for the flower pot time. And if you subtract 1, you get the ball time. Once you have done that, you can sub either of these numbers into the related displacement equation and figure out how far the object, either the ball or the flower pot, has moved. And then you can figure out how far above the ground that is. And in this question, you get 7.1 meters to 2 significant digits. So we've gone over a lot of physics, and you can look that over on your own if you found it a little confusing. What I want to point out in this video is what I was looking for in the solution in general, so that you can nail it on any question I would give you. The solution starts with equations clearly shown. So down here, or up here rather, the equation was clearly shown. Maybe you wrote me a little description, even better, to help me understand what you were thinking. You'll see that all throughout the solution. The equations you use should be the kind of equations that are on your equation sheet. So if you knew, let's say, that this over here was going to be the result, let's say you knew somehow, I don't know, you're a genius, you have a photographic memory or something, and you knew that the solution was going to be 2.2 delta TF equals 4.6. That's great. You're smarter than I am, but you can't start with this at the very top and just write it and expect me to believe that you somehow knew that that's how it was going to turn out. You still have to begin with the displacement here, the large equation for uniform acceleration, the time equation, and put them all together. Show me the substitutions and show me the steps. Don't skip any steps. You're communicating here. I got to know what you were thinking, even though all I'm doing is looking at a sheet of paper when I mark your solution here. Final answer should be clearly shown. Everything should be correctly manipulated algebraically. And if you do all that, then I'm seeing the kind of knowledge, thinking, and application that I need to grant you the marks you want. One last word on communication. We already talked about the diagram, so I'll skip that. Make sure you're using the proper symbols, sig figs, units, vector directions, so on and so forth. You're rounding your answers correctly. All steps clearly shown, and the substitutions are clearly shown. If you can do all these things, then you stand the best possible chance of getting the highest mark that you are entitled to. Now, a couple of other quick things. This question here is in your textbook, and it's just a question that involves really manipulating equations and doing a bit of algebra, but it also involves a little bit of thinking because you have to figure out what's the displacement idea, what's the time idea. Then you got to use a little bit of application. You have to combine those into one equation toward the end and solve. So there is knowledge. You have to know that this is acceleration due to gravity. There's thinking and formulating a plan. You have to put together all of these thoughts. And then application, of course, is joining the displacement idea, the time idea, the balcony idea, and so on. So in class, when I say that most questions involve all three, thinking, application, and knowledge, and it's hard to separate them, that's what I'm talking about. That's why it's really hard, especially this year during the pandemic, to start separating separating problems into this many marks for knowledge, this many for application, this many for thinking, okay? If you want to see a little bit more thinking, I've added something here. Here are 3 additional questions you can try, which would stretch your thinking. Number 1, pick 2 aspects of the movement of the objects that would change if air resistance were a factor. Describe how and why each of these factors would change. So if we were to add air resistance in here, how would the motion of the ball change? What about the flower pot? Would it affect where and when they met? How? Pick some factors, explain how they would change and why each one would change. Number 2, with what initial speed would the ball have to be thrown in order for the objects to meet at the ground? In this question, they met 7 meters above the ground. But what if we wanted them to meet exactly at the ground? What would have to have been the initial speed of the ball? Can you go back and figure it out? And here's one which is a little bit trickier and involves some deeper mathematical thinking. And here's this. It's easy to show that the flower pot strikes the ground approximately 2.4 seconds after it's dropped. You should go check that out. See how long it actually takes for just the flower pot to hit the ground. So imagine this. Imagine if you released the ball 3 seconds after the flower pot was dropped. You and I now know the flower pot's already hit the ground. It's too late. The ball can't catch up. But if you try that number in the equation and you set it up with a number of 3 seconds, not a 1 second delay, you actually still get an answer mathematically. That's because the equations don't know that there's a ground. They just think this is acceleration due to gravity forever. Objects just keep on going. So the question is, how does the math let you know that you have an impossible answer here? All right. You might want to go back and put in the number 3 in place of the 1 in the solution and see what comes up. That's what this question is about. It's asking you, how does math alert you that your answer is unrealistic or impossible, which sometimes happens in these kinds of questions. Anyway, that's it for now. I hope this helps you in getting you to see what I'm looking for when I mark a question and the kinds of questions I can ask, as well as the extensions that make you think a bit more. I hope you also see why it's easy for me to separate communication from the other 3 categories. And because we're in the pandemic right now, and I want to be able to use lots of smaller assessments here, I have to make them all marked similarly. So I'll be grouping knowledge, application, and thinking into basically one category where whatever mark you get applies to each category. The communication I can do separately. And this way, my promise to you of taking your top approximately 10 out of 15 evaluations as a sort of quiz or test mark throughout the semester, and allowing for the fact that you may not be able to attend every single evaluation because of the pandemic, that should work out hopefully to everyone's advantage. All right, thanks for watching, and I'll see you guys in class. Bye for now.